All right, so part two. We talked about independent and dependent events, so now let's talk about actually calculating the probabilities of these events. So I want to take a moment to talk about some of the notation that we're using because it's a little different than anything you might have seen in the past. So for probability, we usually use P of some event like A or B or C or whatever we want to name it. So if we're talking about independent events, the probability of A and B happening is equal to the probability of A times the probability of B. So that's what that means. So if A has a probability of 1/2 and B has a probability of 1/3, we would multiply those two numbers to get a probability of 1/6. Now, if they're dependent events, then the probability of A and B is the probability of A times the probability of B given that event A has occurred. Because remember, dependent means that whatever happened the first event is going to affect the second event. And so we use a special notation to indicate that the second event is dependent on that first event A. And this is also called conditional probability, so you'll see that phrase a lot as well. So that's the notation. The notation is important in the sense that you're going to see it a lot, but in terms of what you need to show me on the test, it's going to be more of the actual numbers that you're calculating. But you'll get really familiar with the notation by the end of this unit. So let's look at a couple examples. So let's look at this first example here. Suppose you're flipping a coin and rolling a 6-sided die. What is the probability of landing on heads and rolling a 6? So we want to call these two events event A and event B. And these are independent because one does not affect the other. Whatever we land on with the coin has no effect on what we roll on with the die. So these are independent events. So let's call event A landing on heads, and event B is going to be our rolling a 6. So the probability of both of these things happening, because they're independent, is the probability of A times the probability of B. So if we break down these individual probabilities, the probability of A, which is landing on heads, well, there's two ways to land, heads or tails, and only one way of landing on heads. So that's 1/2. So then we multiply that by the probability of B. So there's 6 different ways to roll to roll a die. 1 through 6, 1, 2, 3, 4, 5, 6, but only one way to roll a 6. So 1 out of 6. We multiply those two together and we get our answer of 1/12. Multiply the numerators, multiply the denominators across. Now, the other way that you can think about doing this is to think about the fact that probability is number of ways to be successful over total possible ways, successes and failures. So if we think about how many total combinations we have, total possible combinations of flipping a coin and rolling a die, we have 2 ways the coin could land, 6 ways the die could roll, and so 2 times 6 is 12. So just like we did the example yesterday about the sweaters and the jeans and the boots, we multiply the 3 sweaters by the 2 jeans and the 2 boots. 3 times 2 times 2 was, what was it, 12, something like that? I think we might have had 4 sweaters. Anyway, you get the point. So 12 different ways that we could flip a coin, roll a die. So then how many ways could there be heads and then a 6? That's only going to be one way. So 1/12 possible ways, so a probability of 1/12. If you're not sure about the different ways, just think we could have heads and a 1, heads and a 2, heads and a 3, heads and a 4, all the way down to 6. And then we could also have tails and 1, tails 2, tails 3, tails 4, 5, and 6. So 1 out of all 12 ways. Let's look at this next example. So for this example, we've got 3 3 cards that we're selecting from a standard deck of cards. Now, I mentioned in the last video that if you're not familiar with a 52 deck of cards, you want to Google that right now. Look it up, make sure you know how many kings, queens, jacks, twos, fours, etc. that the deck has. Make sure you know the 4 different suits, the hearts, spades, cloves, and diamonds. So make sure you're familiar with it. If you need to have kind of a layout of the 52 cards in front of you as you look at these problems, you can do that. So definitely want to be familiar with those because you're going to see a lot of problems involving a standard deck of 52 cards. So with this deck, what is the probability that all 3 cards are queens? Now, know that 4 queens are in each deck. So if we look at A, when we replace each card before selecting the next card, that's going to be independent. And then for B, if you don't replace it, that's going to be dependent for B. So for both scenarios, we're going to let A be that the first card is a queen, B is the second card is a queen, and C is the third card is a queen. So for that first scenario where we are replacing each card and they're independent, we're just going to multiply those probabilities together. So we know 4 out of 52 cards are queens, so that's for the first one. We put it back, and now we've got a full deck of cards again, so we have the same probability the second time and the third time. Multiply those together, and we get 1 over 2,197. So I know some of you right now are kind of freaking out over the big fractions, but don't, because you're going to have a calculator for this entire test. So you can use your calculator to help reduce large fractions. And so what I did, because even me, I'm pretty good with fractions, but something like 64 over 140,608 is a little intimidating. If you just divide 64 divided by 140,608, and then if you remember, we haven't done this in a while, but if you press math and then choose the first option, which is that one fraction, then it'll actually convert that to the fraction with the most reduced form. Now, it's not always going to work, but it often does. So it's really helpful to try if you get a really big fraction. So let's look at B. B is our dependent events. So we are not replacing it. So notice how we have to take into account these conditional probabilities. So the first card, same as before, we have 4 queens out of 52 cards. But now we're not putting that queen back. So we have now removed a queen. You're assuming that you're successful. So these probabilities, remember, are all based on success over total. So we assume success. So we assume that first card was that queen. So now, for the second card, we only have 3 queens left. And notice also, since we took a card out, we only have 52 total cards left. So both our numerator and denominator get decreased by 1. So now we have 2 queens out. So now we've only got 2 left, and we only have 50 cards left. Multiply everything together and reduce to the lowest term, or the lowest number.